When a star reaches the end of its life on the main sequence, it undergoes dramatic changes. These changes don't just dictate the star's fate, but also the destiny of its orbiting planets. As a star ages, it swells up and expels its outer layers, losing mass. This weakens its gravitational hold, allowing it to destroy or consume nearby planets through intense heat and tidal forces. Our own sun will eventually become a red giant, likely engulfing the inner planets, possibly even Earth. But depending on the solar system architecture, some planets can survive this destructive phase. Gas giants, like Jupiter, have the best survival odds. Jupiter-mass planets that survive around a white dwarf typically follow two paths. Either they are so far away they are essentially unaffected, or they migrate inward after the star transitions to a white dwarf. Let's look at some observed survivors, exoplanets that have made it through their host star's destructive aging process. In 2011, astronomers found exoplanet WDO806-661b, a planet with about 8 Jupiter masses, orbiting a white dwarf on an extremely wide orbit, making it safe from the star's destructive phase. Then in 2020, researchers discovered a Jupiter-sized gas giant, WD1856+534, on a tight orbit around a white dwarf. It's thought to have migrated inward after the star became a white dwarf, having survived the red giant phase at a greater distance. Only a handful of these gas giant survivors are known. This raises a crucial question. Is the scarcity due to observational challenges and detection bias, or are these surviving planets genuinely rare? New research titled Predicted Incidence of Jupiter-like Planets Around White Dwarfs by Mauch Soriano and colleagues examines this very question, using stellar evolution codes to predict the population of gas giants. The researchers synthesized a population of white dwarfs and their substellar companions. They utilized detailed stellar evolution codes to account for stellar mass loss and tidal forces. A key finding is that the predicted fraction of white dwarfs hosting substellar companions in the Milky Way is below 3%, regardless of uncertainties in their initial distribution or stellar evolution. The few hardy survivors share specific characteristics relating to white dwarf mass, the age of the system, orbital separation, and the type of companion. More Jupiter-like exoplanets survive when their white dwarfs have lower masses. Survival peaks when the white dwarf is between 0.53 and 0.66 solar masses. Not surprisingly, orbital separation is critical. Surviving companions typically orbit between 3 and 24 astronomical units, or AU. The survivors in the synthesized population were overwhelmingly gas giants, accounting for about 95% of the surviving companions, as opposed to brown dwarfs. The metallicity of the progenitor star has a powerful effect. Higher metallicities mean the progenitor simply formed more planets to begin with. The strong dependence of companion occurrence on progenitor metallicity suggests that the assumed age-metallicity relation significantly impacts the predictions. Based on recent estimates, the researchers suggest that the fraction of white dwarfs with companions close to the Sun might reach up to 8%. The research confirms that while stellar evolution is devastating, a small, specific population of gas giants can survive. This underscores the complexity of planetary survival around aging stars.